Okay, hello guys, welcome to my video. So today we're going to be solving the October-November 2016 question paper 1-1 for physics. And the question paper is 1 hour 15 minutes long, and we're going to be solving it, explaining in detail what some of the responses should have been. So if you do like my content, please subscribe, and please do comment if you have a specific paper that you'd like to be worked out. Please just do comment in the comment section and put the paper code for that specific paper, and I'll have that worked out. So to start off, we start off with the first question. Okay, so for the first question, we've been asked, what is the order of magnitude of the Young modulus for a metal such as copper? Now, this is a question that revolves around making reasonable estimates. It is assumed, and I repeat, it is assumed that you know these things, right? As a student, as a physics student, whenever you're making reasonable estimates, it is assumed that somewhere, somehow, you have calculated the Young modulus of copper when you are doing something, right? So they expect that you know this answer. So my advice for these kind of questions is, if you do a lot of past papers, you're going to meet questions like these. So if you have never done this question, or if you've never read anything about the Young modulus of copper, it was going to be a very tough question. But basically, the Young modulus of copper is just 10 to the power of 11. So that's basically the Young modulus of copper. But it's a very hard question to just, think of it without having prior exposure to the question. So my biggest advice would be try to work a lot of questions so that you can be able to master them, right? Moving on to the next question, we'll be given the force between 2 point charges, Q1 and Q2, that are distance r apart. And it has been given that we have that equation, F is equals to K1, F is equals to K Q1 Q2 divided by R squared, and been asked to find the SI base units of K. So guys, it doesn't matter what equation you are given. If a question asks you to find the SI base units, make that thing the subject of the formula. So that's the first thing, right? Just make it, okay? Make it the subject of the formula, right? So make it the subject of the formula, right? So we're going to start with F is equals to K Q11 Q22, right? So we're just going to make K the subject of formula. So you know that K, okay, will be equal to F multiplied by R squared divided by Q1, right, multiplied by Q2. So basically that is going to be our expression, because we've just made K the subject of formula. So what are we going to do? Do we know the SI base units of F? We do. Okay, the SI base units of F are kg, right, ms to the power of -2. Do we know the SI base units of R? We do, right? It's a meter, so it's going to be m squared. Do you know the SI base units of Q? What do we know, guys? We know that Q is basically equal to IT, right? And the units of I is A, the units of T is S. So Q will what? Q will be AS, right? So you're gonna say, right, you're in AS, and the units for Q are AS, right? So you're gonna have AS, right, times AS. Okay, so this is going to be your expression, right? So S and S are going to give you S to the power of -2. So this is just going to simplify to kg, right? M cubed, S to the power of -4, and then A to the power of -2. You're going to look for that answer, and that answer is going to be B. I'll move on to question number 3. It's a question for resultant vectors, right? Resultant vectors. And the first thing that we need to understand is to read and understand the question. Most of the times, the question will give you some hints, and we can be able to look at that. So we're given an aeroplane, right? So an aeroplane basically flies at a velocity x, right? So we have an aeroplane that's flying in the sky at a specific certain velocity, and it's moving through still air. So it's a nice calm day. The pilot has nothing to rush to, right? And they're just moving at a velocity x. But when we now have wind, right? We have wind that's coming at a certain velocity v. It's going to affect the aeroplane in some way. The velocity of the aeroplane is going now to be y, right? So y, as you can see, y is the resultant, right? So y, in this case, y is what we call the resultant, right? And it's very important for you to be able to establish that fact. And since y is the resultant, it means I can create an equation. Basically, I can say y is equivalent to x plus what do you have? X plus w, right? So y is going to be equivalent to x plus w, and this is a very important relation that you're supposed to make. So based that you know that y is equals to x plus w, it means that we can now be able to ask ourselves in this question, what is the resultant force, and how can we be able to find it? So guys, there's a skill that I need you to learn, right? It's basically a skill of how do you connect vectors. So we have a very special method that is known as the head, right? So it's basically known as the head to tail, right? Head to tail method, right? It's a very, very important method that a person is supposed to know if they're doing AS physics, right? So the head to tail method, right? So how does this method work? So basically, the head to tail method says if you have two vectors, right? So if you have two vectors, so I'm going to put two vectors here, right? So if you have this vector, right? This is vector 1, and you're going to have another vector. So this is what we call vector A. Then we're going to have another vector, which is vector B. So we're going to have two vectors, vector A, then we're going to have vector B, right? It is assumed that if you are to connect these vectors, you connect them head to tail, right? So if you have as one vector and another vector and you want to connect them and find the result, you're going to connect them head to tail. So if I have this vector, right, this is the tail of this vector here. We have the tail of this vector, then that is the head of that vector, right? So basically, we're just going to connect this vector head to tail, right? So we're going to take the vector, and after taking the vector, we're then going to connect it head to tail, right? So you take this vector, and you're going to take this tail and connect it to the head of that vector, right? So if you have a vector like this, you have now connected these two vectors head to tail, right? The head of one vector is now connected to the tail of the other vector. Your resultant, right? So you had two vectors, you had vector A, right? You have vector A here, and then you had vector B, which is now over here, and you've connected those two vectors head to tail. Your resultant vector is going to come from the tail of one vector. So your resultant vector has to come from the tail of one vector. So it has to come from this tail and go to the head of the other vector. It has to go to this head of the other vector. So what is it? What is going to look like? So basically it's going to come here, right? And then it's going to go here, right? So basically this is how you're now going to connect them. So I've just connected them head to tail, and then this is going to be my resultant force. So whenever you have two vectors, vector A and vector B, you're always going to connect them head to tail. Head of one vector, tail of the other vector. Your resultant is from the tail of one vector to the head of the other vector. So basically that is what we're looking here. From the tail of one vector to the head of the other vector, where Y is the resultant. So if we start with A, right? If you look at A, we want to add Y, we want to add X and W. Look at this. I want you to look at this, guys. X is going up, right? X is going up from this question. And as X is going up, if you look very carefully, X is going up, so it's going to go up like this. So X is going to go to the head, all right? So the head of X is going to go to the tail, which is very correct, right? If you look at this scenario here, this is a head to tail that's going on here, that's okay. Then the resultant of Y is going to come from this tail of this vector to the head of the other vector, and that's okay. So our answer is going to be A. But again, I always say it's not about the correct answer, it's about also explaining why the other answers are wrong. So if you look at B, that's not what's happening, right? Because Y, if you look at this, W, this is not okay, because the head, the tail of W is going up here, the tail of X is also going up here, meaning they're not meeting head to tail. The same is happening with C. They are not meeting head to tail. The same is happening with D. They're also not meeting head to tail. So our answer therefore is going to be A. Move on to the next question. We've been given a voltmeter that gives readings that are larger than the true value, right? So you have a voltmeter, it's a very fancy equipment, right? And it measures voltage, how much work is going to be done in moving between point A and point B. But we've been told that it gives readings that are larger than the true value, and it has a systematic error. So guys, underline important terms here. So we have this systematic error, right? What are the information am I given? I'm given that it's larger than the true value. So those are the two things that I need to be keeping care of. I need systematic errors and I need larger values than the true value. Another thing that I'm also seeing here is that it varies. Okay, it varies. The systematic error is not constant. So you first need to know how the systematic error is going to affect this and how the systematic error is going to work. So the mere fact that it's giving readings that are larger than the true value, if I were to look at my answers, definitely without even skipping a heartbeat, I would say C is wrong, right? Because if you look at this, O and O is passing through the origin right here, and that's wrong, right? It can't pass through the origin. That doesn't make sense. So it means that if you were to look here, right, because of the virtue of what is going on here, right, because it's passing through the origin, it basically means that it is wrong, right? Then if you look at D, when we're told that the readings are larger than the true value. Then if you're to look at here, right, if you're to zoom in and if you're to analyze the situation, if you're to analyze what's going on here, we have one value, right? We have a value, a specific value of the meter reading, but look at the actual voltmeter reading, right? The true value is actually higher than the meter reading, and that's wrong, because the question is telling me that the meter reading must actually be what? Must actually be larger than the true value, meaning that D on that virtue is going to be wrong. So I'm left with B and A, right? They're fighting to see which one is correct. If you look at A, it's true, right? I have 1, right, as my true value. I have a slightly bigger actual value, sure. If you look at this, I have 1 as my true value. I have a slightly bigger value. That's correct. I have 2. I have a slightly bigger value. That's correct. But if you look at this doesn't vary, right? Because systematic error is saying if you measure a certain error, right? Let's assume here, if this was 1, right? And this is, I don't know, let's say 1.2, right? It means my error is going to be 1.2 minus 1. My error is going to be 0.2, right? If I look at this scenario, I have 2, right? If I look here, I have 2. Then here I almost have 2.2, right? So I have 2.2 minus 2. My error is going to be 0.2. That's a constant error, guys. I'm always deviating by the same amount. But I've told that this systematic error varies. It means if I have an error first time, the second time is going to be a bit different. And if you look at this, here I have 1, right? Here I assume maybe, let's say I have 1.3, right? So this is for B. Then for A, let's assume I have 1.3. So I'm saying 1.3. But then if I subtract 1, I'm going to get 0.3. But if I look at this, when it's slightly higher, guys, I have a 2 here. Here I have about 2.5, right? I have 2.5. Basically, I'm just estimating. It's not accurate, just an estimation. But you can see that the error is varying, right? So the answer is going to be A. On the virtue that the error has to change, the error has to vary. So it means that the answer has to be A. Very important for you to be keeping note of that. Move on to the next question. We've been given a student, right? I'm going to call her, I don't know, let's say Mary, right? So Mary is going to use a cathode ray oscilloscope, right? Fun time for Mary. So a cathode ray oscilloscope, as you can see on the screen, basically gives a waveform of a certain wave, right? And we've been told that she sets the time base, so Mary is busy tuning the time base, so that 1 centimeter represents 5 milliseconds, right? Very clever. So 1 centimeter represents 5 milliseconds, and you want to find the period. So the period is the time taken for one complete wave cycle. So one complete wave cycle starts here, right? It's going to go up, it's going to go down, then it's going to come to the equilibrium position. So basically, this is going to mark one wave cycle, right? This right here is going to mark one wave cycle. But how many of these do I have, right? I just made one, right? But if I go again, right, I'm starting here. If I go again, up and down, here I have another one. I have 2. Okay, I can do that again. Okay, I can do that a third time. I'm going up and down. I arrive at equilibrium position. I have 3, right? I can do that again, right? I can also go up and down as well. So if I go here, up, but I don't go down, right? So it means that basically I have 3.5, as you can see from the different colors, I have 3.5 wave cycles, right? 3.5 complete wave cycles. So that's very, very important information that we need to take care of. So I have 3.5 complete wave cycles, right? That's very important for just me to have that in mind. But how much space do these guys take up? How much space are they taking up? Well, if you look at that, we have 10 centimeters. So if 1 centimeter is going to represent 5 milliseconds, then 10 centimeters, as is in the graph, is going to represent 50 milliseconds. Isn't that important, right? So basically, if you were to look at this, so in 10 centimeters, you have 3.5 cycles. So basically, how much does one cycle occupy? So it's going to be 50 divided by 3.5, which is 3.5. That's basically going to give you 14 milliseconds, which is 1.4 times 10 to the power of -2. The correct answer is going to be D. Very important. Okay, a cyclist pedals along a raised horizontal track. So it's doing some cycling, and if you have done cycling, you probably haven't done this, right? Because this is crazy, right? Literally, it's some stunt stuff that's going on here. But basically, we have a cyclist that's pedaling along a raised horizontal track, and at the end of the track, that cyclist travels horizontally into the air onto a track that is vertically lower. Okay, so we want to find the horizontal velocity v of the cyclist at the end of the track. So basically, we want to find what velocity will he be moving at the end of the track. So basically here, we just want to find the vertical velocity that is going to be here. So what do we know, guys? So my biggest advice for paper 1, if you're stuck, write what you know, what information are you given, and how can you go from there. So what do I know? I know that for projectile motion, the range, which is 6 here, the range is actually Vx, okay, multiplied by t, right? That's one of the equations that I know. What else do I know? I know that S is equivalent to ut plus half, okay, at squared, right? This is a very important relationship. But I know in this case that ut is going to be 0, right? Because ut, by its nature, u is 0, the initial u, right, in the y, because remember this is for the y-axis. And if you look at this, if the cyclist is going to go off with a certain velocity like this, right, in the y is going to be 0, right? There's nothing in the y here. There's nothing that is going to be present in the y, so it's going to be 0, right? So basically you'll be left with s. With s is going to be equal to half, okay, at squared, right? So I have two equations here, guys. I have two equations, and those are the equations that I'm going to use. Okay, so I have equation 1, which is this, right? And then I have another equation, right, which is this. Okay, so I have two equations, right? Let me enlarge this, right? So these are what I'm going to use to continue with my calculation. Okay, so what's next? What next? Next is substitution, right? I know 6 based from equation 1. So this is my equation 1. Then this is my equation 2. So I know that 6 is going to be equal to Vx multiplied by a certain time t that I don't know. But I know from this one that it's going to be 9.81 since they're on Earth, and the acceleration due to free fall is going to be 9.8 because of their weight. Right, so I know that by using equation 2, I know that 2 by 2 divided by 9.81, the square root of that is going to give me the time, right? So because of the calculation that I've made, I'm going to get a time of 0.6385 and so on and so forth, right? So basically that's going to be my time, right? So basically this is going to be the time that is going to be taken by the cyclist. So I have t. So how do I find Vx? Very simple. So Vx, okay, is going to now be just 6 divided by the time, 0.6385 and so forth and so forth. So Vx is going to be 9.4 meters per second, right? So the answer is going to be B. Okay, moving on to the next one. An astronaut is on the moon, right? So we are going to the moon, guys, and we have an astronaut who's busy walking in the moon. Now the astronaut throws a ball. Now this is a very fun astronaut, right? He's playing, I don't know what he's playing, but he has a ball on the moon, right? So he has the ball, he throws it, and the initial velocity of the ball, right, has a vertical component of 8 and a horizontal component of 4. So we want to find the speed after 9 seconds. So we want to find the speed 9 seconds after being thrown. So basically, 9 seconds after being thrown, right, it's going to look like this, basically. So if you have 9 seconds and you have thrown it, we want the velocity that's going to look like this, right? So if you're going to look at this, right, there's going to be a velocity that will be like this, because the velocity is going to vary, right? It started like this, right, when we're here, right? So our velocity was like this, then it started bending and tilting and tilting. It reached a point where it was at the top, where it was 0 in the y, but maximum in the x-axis, so it was something like this. But now we have arrived at this point where it's now going to be like this, right? So basically that's what we're working on with right here. So it's something now like this. So I just want to find this speed that is now acting on this ball. But this speed consists of two directions, right? There's two directions, because as you can see, it has okay, let me put it. There's a direction in the x, like so, right? It has a direction in the x. And it also has a direction in the y, like this, right? So you have two directions, a direction in the x and the direction in the y, and then this is our resultant vector. So if I find the velocity in the y, if I find the velocity in the x, I can basically find the resultant of this by using Pythagoras theorem, because this is v, right? This is vx, this is vy. So it means that to find v, v squared is going to be equal to vx squared plus Vy squared, right? So I'm going to use this equation and it's going to guide me to do everything. So Vx is going to be constant, right? So Vx is always constant. Whenever you're talking of projectile motion, right, it doesn't change and it's always constant with a value of 4.00 meters per second. But it's Vy we need to find. But we have equations, guys, that can allow us to find this, right? I know that Vy is going to be equivalent to Uy minus G times T, right? So Uy, the initial one, is going to be 8 minus the acceleration, which is 1.62 times the time is 9 seconds, right? Which is 9 seconds. If you close that, we're going to get a Vy of negative 6.58. Okay, so basically this is the velocity that is present when you're now going down. So for you to find V, it would just basically be the square root of, right, negative 6.58 squared plus 4 squared. And then your V is just going to be equivalent to 7.7 meters per second. Right, very important. So it's going to be 7.7 meters per second. Move on to the next question. Question number 8. A car is traveling at a constant velocity. So we have a car that's traveling, right? So a driver is moving a car, and then the driver sees an obstacle. Let's assume maybe it's a deer, right, or an animal. They see an obstacle and they want to stop, right? So they quickly step on the brakes, and then we're given the variation of their velocity. So we want to find how far it travels in 5 seconds after seeing the obstacle. So basically this is just, guys, the area underneath the graph, right? The area under which graph? Where do they start their brakes? They start their brakes right here. So we just want to find this area as a whole, right? The area where they're applying their brakes. So it's basically just this area, right? Okay, that's it. We just want to find this area. Okay, so how do you find this area? Guys, this is a triangle. Look at this, guys. We have two things. We have the height. We have the height h. What else do we have? We have the base b. Then what do I know? I know that the area of a triangle, right? The area is going to be 1/2, right? The base times the height. So it's going to be 1/2. What is my base? My base is 5.0 minus 0.8. That's 4.2. Multiplied by my height is 20. In this case, multiplied by 20. So half of 4.2 by 20 is going to give me an answer of 42 meters. Yay. Okay, so the answer is going to be B. I'll move on to question number 9. We're given another car, the same car. Let's bring back our car, right? That's traveling and is going to meet traffic lights. So it's going to meet traffic lights, and when the car's traffic lights changes to green, it changes to green, the driver then presses on the accelerator, and the horizontal force acting on the car varies with time. So the driver was stationary, presses the accelerator and starts moving. So initially, the driver has no acceleration based off of this this point. From this point to this point, there is no acceleration. So basically, the acceleration is going to be 0, right? But I know that if I'm given a speed time graph, right? One important feature that I need is essentially the gradient, right? Because I know that the gradient of a speed time graph actually symbolizes what? Actually symbolizes acceleration, right? This is a very, very important fact that I know, because if I can find the gradient of a speed time graph, I can basically find the acceleration. So here, acceleration is equal to 0, gradient is also going to be equal to 0. So yeah, all graphs are correct in that respect. But the second part, we're going to have a constant force. Okay, I know that F is equal to ma, right? Mass times acceleration. So F is going to be equal to mass times acceleration. So the force is going to be constant, right? So since F is going to be constant, right? So since F is going to be constant, what does it mean? It means that the acceleration is also going to be constant, right? F is constant, A is constant. So it also means that the gradient, right? The gradient is going to be what? The gradient is also going to be, guys, come on. The gradient is also going to be constant, right? So where do we have a constant gradient? Is this gradient constant? No. Is this gradient constant? No, guys, look at this. This is not constant. Is this constant? No, that's wrong. So the answer is going to be A, right? Very important. Okay. Move on to the next question. Question 10. A beach ball, So we're going to the beach, guys. So we're going to stop physics and go to an actual beach, right? As you can see on the screen, right? So this is the beach, and at the beach we have a beach ball, which is going to fall from a high hotel window. So this is a very lucky person. They have gotten the opportunity to go to a beach. I've never been to a beach before, but I think it's a very fun experience. They're about to throw it off the window. They forget one thing: air resistance is not negligible. So we've been asked to analyze for this guy what's going to happen to the acceleration of his ball, right? Okay, well, I'm just going to work this out, right? But come on, guys, you know, he gets to go to the beach, gets to go into a hotel. We can't even take care of the ball. This is crazy. Okay, so which graph shows the variation of the time and the acceleration? So get this, guys, get this. I want you to get this concept clearly. If you have a ball, right, there are two scenarios. If you have a ball, we have ball A, okay, ball A. Then we have ball B, right? So I'm going to put it here. Okay, ball B. I have two balls. Okay, so I'm going to consider two scenarios, right? The first scenario is going to be air resistance is negligible. So in the first one, air resistance, okay, air resistance is going to be negligible. So I'm not going to consider air resistance. So I'm going to have three positions. So maybe position 1, then I have position 2, then I'm going to have position 3. Okay, something like this. Then for the other one, air resistance is negligible. So air resistance is not. Okay, so negligible is not. So in this case, air resistance is not negligible. Okay, so we're considering air resistance. Negligible just means we're considering it. Not negligible means we're not considering it. Again, we have three positions. Position 1. Okay, position 2. Okay. So we're going to introduce forces. What forces are going to act in these systems and why and how do we deal with them? Okay, so looking at this, if the ball is about to fall, right, the only force that's going to act on this ball is the weight, right, the weight of the ball. So this arrow is going to symbolize weight. The red arrow always going to symbolize weight. So let me reduce its size like so. Okay, let me make it a bit smaller. Okay, something like this. Okay. Whoa, why is it getting bigger? Okay, like this, right? So this is going to symbolize weight. Okay, so as they're about to fall, they're both going to have weight. Okay, like this. And weight is not going to change. So in all scenarios, we are always going to have weight, right? So we're going to have weight here. We're going to have weight for that same ball also here. Okay, so we're also going to have weight here and weight here. Okay, then we're also going to have weight here. Okay, then also going to have weight in this scenario here. Okay, but I'm going to introduce another variable, which is going to be air resistance, right? I'm going to introduce air resistance here. If air resistance is not negligible, it means it's going to act, right? It's going to act up like so, okay? But it's also going to increase. Okay, we're going to talk about why it's increasing in a moment. Okay, so something like this, right? Okay. Okay, until they become equal. Okay, so guys, these are basically the two scenarios you're ever going to see. Well, there could be other scenarios, but you know, in as much as Cambridge is concerned, they're gonna ask you a lot of questions about this. So I want you to understand and lock in on how this is going to work. Okay, if air resistance is not negligible, the weight is never going to change, right? The weight is acting down. It's always going to be constant, right? So it means that since F is going to be equal to ma, the only force acting is going to be the weight, which is going to be contributing the mass and the acceleration. And if this doesn't change, the acceleration doesn't change, and the graph is going to look like this, right? So for B, the scenario B, the graph is going to look like this. But for A, you know, so guys, these are wrong, right? So for A, right, when you're considering A, I want you to think of this. As it begins to fall, there is no velocity whatsoever, right? It's just starting to fall. So it's going to have an acceleration due to its weight, right? Acceleration due to its weight. So the first acceleration, W, is going to be equal to its mass times its acceleration for this specific scenario. But as it begins to fall, the air resistance begins to build up, right? So the resultant force is now going to be the weight minus the air resistance, going to be equal to your mass times your acceleration, right? As the velocity increases, the air resistance is also going to increase. If you're moving faster on a bike, you're going to feel the wind much more because the air resistance is increased. So as the air resistance increases, it essentially tells me that from this scenario, this resultant force is going to decrease. And in this case, if W is going to be equal to R, the resultant force Fr is going to be equal to 0, right? There's now going to be no resultant force, hence my acceleration is going to be equal to 0. So if A resistance is not negligible, it starts from a very high value, which is 9.81, contributed by its weight, okay? As the A resistance builds up, the resultant force decreases, reaches a point where the weight and the resultant force are equal, hence the acceleration is going to be 0. So the answer is going to be C. Okay, our car is back. Wow, these guys really loved cars in this exam. Okay, a car is a mass m. Okay, so this car, as you can see, has a mass m. And if a person, a guy, trying his best to push it with a force F. So we have scenario 1. Okay, in scenario 1, they're going to push with F is equivalent to, the mass is m, the acceleration is A. But they're going to experience a resistive force. We've been given which expression gives the constant resistive force, meaning that the resistive force is not going to change. Okay, so I'm going to try something fun here. I'm going to let the resistive force, right, B, right, BR. Okay, so it means that if a person exerts a force F, so it's just going to be F minus R, that's going to be equal to the mass times the acceleration. Okay, that's case 1. Okay, case 2. Case 2 is going to be here, right? The person is going to exert 2F, but it's going to cause 3ma. The acceleration is now 3 times. Again, our resistive force is R, so it means that 2F minus R is going to be equivalent to 3ma. Guys, this is a simultaneous equation. We try to find R. So if you look at this, this is equation 1, this is equation 2. Let's solve them. Okay, so F is going to be equivalent to ma plus R. So I can put this F and substitute it here. So I'm going to have 2, open bracket, ma plus R minus R being equivalent to 3 mass times acceleration. So this is going to be 2 ma plus 2R minus R being equivalent to 3 ma. So R is going to be equivalent to 3 ma minus 2 ma. Therefore, R, the resistive force, is going to be equivalent to ma, and the answer is going to be A. Very important. Okay. A box is resting on the ground. Question 12. Newton's third law implies that, so the great Sir Isaac Newton came up with 3 laws of motion: first law, second law, and third law. And the third law states that for the sum of the, and the third law states that, you know, for every action there's an equal but opposite reaction. If body A exerts a force on body B exerts an equal but opposite force on body A. So basically we want to find Newton pairs, basically. So in this question we have 2 pairs, right? If we have F, okay, if you look at this, if we have Q, which is basically the force that the earth, right? So it's the force that the earth has, so it's earth on box, sorry. And then S is going to be the force of box on earth, right? So since the box contains mass, right? And since the earth also contains mass, the earth is going to push the box down, right? Causing a force Q. The box also going to try push the earth up, causing a force S. And these 2 forces have a relationship. Okay, these 2 forces are related. They're brothers. They're known as gravitational forces. Okay, gravitational, or okay, gravitational. Okay, gravitational forces. Okay, we have other 2 forces, P and R. So if you look at these guys, R, P is going to be the force that the box, right? So the box is going to push the floor, but the floor is going to push the box. So it's floor, right? You can say floor or you can say ground, right? Depends on what works. So it's either floor or it's going to be ground on box, okay? But R, this force is going to be box on floor, right? And again, These two forces are related. They're twins. They're related, equal but opposite. And these are known as normal contact forces, normal reaction forces, right? So these are known as normal contact forces, right? Very, very important forces. So we now know our brothers, our twins, Q and S, P and R. So we have in this question from question 12, P is equal to Q. P and Q, they're not related. It's P and R that's related in Q and S. Q and P not related. It's again Q and S. R and S not related. S and Q, they are related. They are equal, sure. Opposite, yes. Gravitational forces, yes. So the answer is D. Question 13. Two spheres travel along the same line with velocities u1 and u2. They collide, and after collision, their velocities are v1 and v2. Okay, which collision is not elastic? So guys, I want you to know, what is an elastic collision? Okay, so take time to think about it. What is an elastic collision? So basically, an elastic collision is a collision in which kinetic energy is conserved, momentum is conserved, and relative speed of approach is equal to the relative speed of separation. So if a collision is elastic, no energy is lost, right? Doesn't really happen in real life, but let's assume it did. And in this case, you want to find which equation is not elastic. So we're going to compare two things, right? We're going to compare the relative, okay, the relative speed of separation, right? So this is the claim that the relative speed of separation must be equal to the relative speed of approach, okay? The relative speed of approach. Okay, so this is the claim that we want to make. It's a very bold claim, but I'm going to go with it. So the relative speed of separation is going to be equal to the relative speed of approach. But we have to figure out, how do we calculate the relative speed before collision or after collision? Here's my trick. I've been using this for a long period of time. It's always given me results. Okay, if objects move in the same direction, right? If objects move in the same direction, to find the relative speed, you always subtract. Okay, lock in. If objects move in the same direction, you always subtract. Why? Okay, a simple trick, subtract, right? Same direction, subtract, okay, right? I hope that makes sense, right? But why is this so? Okay, imagine you have car A, right? You have car A and you have car B. They are moving in the same direction, right? Car A is moving at 30 meters per second. Car B is moving at 20 meters per second. But look at their relative speeds. These guys are different by 10 meters per second. That's their relative speed. Because if B travels 30 meters in 1 second, C has traveled 20 meters. So relative to each other, they have a difference of 10. But if they are moving in opposite directions, okay, if they are moving in opposite directions, what are you going to do? You're going to add. Okay, how did I memorize this? I just knew this. Look at the situation, right? These two P's sort of are similar to this D situation going on, right? So if they are opposite, you add. But why is it? Let's go back to our car A and B. If car A and B are approaching each other, let's assume with 7, the other one with 5. The one with 7, we're going to say 7 plus 5 is going to be 12. Because think of it, this one is moving with 5 and this one is moving with 7. So according to this, it's more like it's 12. Because if they're going to reach a common point X, right, this B is helping it by moving 7. A is also going to move 5. So it's going to be 12. The effort in moving to point X is now going to be 12, right? But if that's so hard to conceptualize, my advice to you, same direction, subtract, opposite directions, you add. You always get the mark. Okay, so if we're going to look at this, before collision and after, it's always same direction. So always you're going to what? S, subtract. Okay, so in this case, bigger minus smaller. So it's negative 5 to, okay, let's just say 2 minus negative 5, that's 7. Negative 5 minus negative 2, that's negative 3. That's wrong. So the answer is correct, right? That's wrong because it's not elastic, but it's correct. Okay, 3 minus 3, that's 6. 6 minus 0, that's 6. That's correct. 3 minus 2 is 5. 6 minus 1 is 5. That's correct. 5 minus 2 is 3. 3 minus 6 minus 3 is 3. That's correct. So the one which is not elastic is the one where they are not equal. And that's going to be A. So guys, I want you to log this in. Whenever you see a question that is relative speed of separation, you're going to what? To subtract them if they are moving in the same direction. If they're moving in the opposite direction, you're going to add. And if the ones you've done for before is equal to the one after, separation is equal to approach, that means the collision is elastic. If not, not elastic. Move on to question 14. A submarine has circular windows of diameter 0.30. Circular windows, and we have it going to experience a maximum external pressure. So what do I know? Just start with what you know. Time is not on our side. Pressure is force divided by area. That's where I'm starting here, guys. Okay. Force is going to be equivalent to pressure times area. Okay, very important. I'm making relations here. Okay. The pressure is going to be equivalent to 660 times 10 to the power of 3. Then the area is going to be pi r squared, which is pi d squared over 4. Okay, pi d squared over 4. Okay, so we have 660 times 10 to the power of 3 times pi. Our diameter is 0.3 squared divided by 4. That's going to give me a force of 47,000 newtons. Approximately, guys, approximately. Punch this on your calculator and see it for yourself. So force is going to be equal to pressure times area. So water is going to apply force on these walls, right? And to crack the window, we need this amount of force because it's going to be the maximum pressure it can handle. So the answer is going to be A. Question 15. 4 beams of the same length each have 3 forces acting on them. Which beam is both, very important, underline keywords, guys. Both what? Zero resultant force. Okay, that's the first one. Then what's the other one is zero resultant torque. So we have to look at those two scenarios. And you know torque, guys, sum of clockwise moments must be equal to the sum of anti-clockwise moments. Okay, so basically that is what I want to test here. So let me go on my expedition. Okay, question A. I have 90, I have 30, I have 50. Above here it's 80, 90 down. That's wrong, right? The resultant force is not equal. 36, 70, that's 106, 106, that's correct. 28, 35, 63, 63, that's correct. 42, 70, 112, 112, that's correct. So B, C, and D are correct with regards to resultant force. But are they correct with regards to resultant torque? Let's find out. So we have this formula that says the sum of the clockwise moments must be equal to the sum of the anti-clockwise moments. Okay, so sum of clockwise moments must be equal to the sum of the anti-clockwise moments. So, okay, this is going to be very important. We're going to use it a lot, right? So we need it here, right? Let's first start with B. Okay, so I have 36 on that side times 0.5. That's clockwise, okay? And then that's going to give me 36 times 0.5. That's basically half of that. That's going to give me 18. Okay. Then on this side, I have this, which is anti-clockwise. That's 70 times 0.3. That's going to give me 21. These two are not equal. So A is wrong because it's not 0. Okay. We go to this one. I have 28 times 0.5. That's going to give me 14. I have 35 times 0.3. That's going to give me, what do I have? 10.5. Are these equal? They're not equal. That's wrong. I have 42 times 0.5. That's going to give me 21. I have 70 times 0.3. That's also going to give me 31. Yes, I found it. The answer is D. That's physics for you guys. You have concepts that you have. You're going to apply them and try to solve a common problem. So physics, you have concepts, but you have to apply them in solving a particular question. Okay, but guys, I'm just going to imagine what might happen, right? Imagine what might happen. I have a beam, right? This beam might do two things, right? This is so fun because I want you to think of this, right? This beam might slide down, okay? Because literally it's going to slide down. So in order for it not to slide down, we need a frictional force that will be acting upwards, like this, right? Because initially it was supposed to fall down. So since it's not falling down, we need a force that's going to oppose it. But this boat needs to exert a force up that's going to support what was supposed to happen in the first place, okay? Then if we look at here, right, it was supposed to slip off the air conditioning unit, but it's not, because the boat is going to exert a force in this direction, right? It's going to exert a force in this direction, okay? We're done with friction. So whenever you have friction, imagine it can be a ladder, right? A ladder problem, very, very common problem, right? If the ladder is going to fall, it's going to slip like that, right? So the frictional force has to be in that direction, right? So basically that's how you think of this. And then for the reaction force, it's going to press on the wall, and the wall is going to say, no, I want to press back, right? I don't just, get to be pressed without pushing. So it's going to push back, retaliate. So it's going to push back like so, right? The same thing is going to happen here, right? The air conditioning unit is going to push up, right? And then we're going to experience also a force pushing down, right? Okay, like so. We have our force pushing down. So basically this is what's going to happen, right? The beam is going to try to fall in this direction, right? Going to try to fall in this direction. So we're going to need a force that's going to oppose that. The beam is going to try and fall in this direction, right? Try to move down. Then we're going to need a force that opposes that. Then the beam is going to push in. So we're going to need a force that's going to oppose that. Then the beam is going to be pushed up like so. Then we're going to need a force that's going to oppose that, which is going to be acting down, right? Because it's going to press up. So a force is going to press down, right? Hope it makes sense. So we're going to look which answer best suits the scenarios, but definitely going to be B. Very important. And if you look at this, it doesn't make sense. How is this correct, right? But how is this acting down, right? That doesn't make sense. Even here, why is this force in? That doesn't make sense, right? At the same time, why is this also in? That doesn't make sense. Okay. 17. A hydroelectric station, right? We have a hydroelectric station that's going to use gravitational potential energy. So it's going to consist of a dam, right? We have a very popular dam in Zimbabwe, the Kariba Dam. Very good source of hydroelectric power station. It's a very good, we have the Kariba Dam. It's a very good source of hydroelectric power. And we've been told that it's going to use gravitational potential energy, okay? In one particular station, with a very particular station, we're given the mass flowing per unit time. In 1 second, how much mass is flown. And the water is falling through a height of 120. So it's going to fall through a height of 120 meters. So the electric power that is generated is 100 milliwatts. What is the efficiency of the station? So guys, output, okay, divided by power input. Okay, or efficiency can be described as energy, right? Energy output versus energy input. Okay, so it's energy output versus energy input. Okay, very important for you to be thinking. So with energy output, energy input, power output, power input. So as a student, you're studying, right? Your whole goal is to pass your Cambridge exams, get to college, or I don't know, find a job or do something like that. That's probably a goal that you have, right? And as you'll be studying, you want to get something out, a result or something like that, right? But you're going to put some effort in. So the ratio of what you get out versus what you put in measures your efficiency as a student. If your efficiency is you get very good grades and you put a lot of effort, so you're going to have a very high efficiency. For some people, they get very good grades, very low input. They have a very extremely high efficiency, right? So efficiency is just a matter of comparing what you get out versus what you put in. So as a student, I advise you, think about it. What do you exactly get out, right? And is it representative of what you get in? What is your efficiency, basically, as a student, right? So, but for this water station, right, the efficiency is going to be the power output divided by the power input. We have the power output, 100 milliwatts. What we don't have is the power input, and that is what you want to find. Again, that's the problem that we want to solve. So power input. So it is power, power power input, right? Sorry, power input is going to be equal to, right, energy. Power is energy divided by time. Okay, so energy is mgh because it's gravitational potential energy. Your time is t. Then I can group these guys up, right? I can group these guys up. Okay, so I'm gonna have m over t, right, times g times h. Okay, so m over t, that's going to be 1.5. So that's going to be 1.5 times 10 to the power 5 times 9.81 times 120. That's going to give me an answer of about 176.581234. So it means that if I go back to my question, how do I find my efficiency? It's going to be my power output, 100 times 10 to the power of 6 mega. Remember your prefixes, guys, please. That's very, very important to be. Remember your prefixes, guys, very important. And then we have 156, 58, 1, 2, 3, 4 times 100. What's that going to give you? That's going to give you 57%. Not that efficient, but it will do. It will do. An engine transforms thermal energy into mechanical work. With a big engine, transforms thermal energy. You put coal, for example, that's your heat source. You're chucking in coal into the machine, and then it's going to do some work. Then it's going to give out some heat as output, right? Then it's going to do some work. So again, efficiency. These questions are related, guys. Look, we just solved the equation of efficiency a few seconds ago. Power output over power input. So in this case, it's going to be what work do you get out, right? What's useful versus what do you put in, Q in. Your answer is going to be C. Question 19. We'll be given a truck, okay, of mass 500 kilograms. So we have a truck that's going to move from rest at the top of the section. So it's going to move down, and the frictional forces acting on that truck is going to be 250 throughout its journey. We want to find the final speed of the truck. Okay, what do I know? And it's here, it's containing some energy, right? It's containing an energy that is known as gravitational potential energy. Okay, but as it falls, it's going to be used up. So the gravitational potential energy is going to go to two things, right? Number one, it's going to go in increasing the kinetic energy. Okay, that's some of the place it's going to go. Then some of the place it's going to go in overcoming friction. Okay, in overcoming friction and in kinetic energy. So overcoming friction as well as in kinetic energy. So that's very, very important for you to be able to figure that out. So first, what I need is how much GPE do I even have, right? How much GPE do I have? How do I find that? It's mgh. That's going to be 500 times 9.81 times the height. What height do I have? A height of 30. So my gravitational potential energy is going to be 147,150 joules. Okay, and then I'm going to look at how much energy has been done. So in work done against friction is going to be the force that you have times the distance that you're going to move, right? So the work that we're going to do in overcoming friction, right, is going to be, okay, so the work done is going to be force times distance. The force is 250 times the distance, which is 400 meters. The distance is this, guys. This is the distance that has been moved, right? Not this, right? It's not moving vertically, it's moving horizontally. So we need the horizontal distance, okay? So we're going to get 250 times 400. That's going to be 100,000. So where is the rest going? The rest is going in providing kinetic energy. So it means that my good old kinetic energy, okay, where are you, guy? My good old kinetic energy is going to be 147,150 subtract 100,000, okay? Then that's going to give me 47,150 newtons. But what do I know? I know that KE is 1/2 mv squared, right? It's 1/2 mv squared, okay? So it means that 47,000, right? So if I'm looking at this, it means that 47,000, sorry, not newtons, it's joules. Okay, here we have joules. Okay, So we have 47,150 by 2 divided by 500. The square root of that is going to be my V. Therefore, my V is finally going to be 14 meters per second. Very important. So the answer is going to be B. Move on to question 20. Which conditions must apply for the work done by an expanding gas to be P delta V? So we know that work done is going to be equal to P delta V. So the biggest rule, the biggest rule, as you can see, this is change in volume, right? This is change in volume. Okay, and then this is pressure. So again, I need constant pressure. This is a must, guys. You need constant pressure. So it means that your pressure must always be constant. It's a must, right? So that will be something that I'll be considering. Move on to question 21. We'll be given a metal wire that is stretched to breaking point. And the force extension graph is plotted, which graph represents the elastic region. So basically, elastic region is that it's elastically enlarging or expanding extending, but it returns back to its original position. So basically, this is the elastic region, right? So meaning B is wrong. This is indeed the elastic region. So all of these are correct. But the work that you're going to do, work done, is basically the area underneath the graph. So the work done is just the area, right? That is going to be under the graph. So the area that is under graph, right? The area under the graph, under this graph specifically, is the one that's going to be your work done. So basically, this whole area is going to be your work done. Okay. This whole area as a whole. So since you're gonna break, right, it's gonna break at this point, right? This is the point that is gonna break. Okay, point X here. So it means that we need to go and reach that point. So this is the whole work that we're gonna need. So the answer is going to be D. Very important. Okay. Question 22. A copper wire hangs vertically from a fixed point. A load is attached to the lower end of the wire, producing an extension X. The wire obeys Hooke's law, which single expression gives an extension of 2x. Okay, I know that F is equivalent to kx. Okay, but I also know that the Young modulus E or Y is also going to be equal to stress, right, divided by strain. Okay, how much stress occurs, how much strain has happened, and stress is the force per unit cross-sectional area. Strain is the extension per unit original length. So I'm going to have F times L divided by X times A, right, being equivalent to my E, right? Okay, so that's very important. And then what I'm going to say is that E, right, times A times X, right, is going to be equivalent to F times L, right? And from this, if everything is constant, right, if E is constant, if F is constant, if L is constant, but it's the same load, it means that A should be inversely proportional to 1 over X. Okay, because A and X are inversely proportional, everything is constant, right? So if you halve the area, so if you're going to halve the area from inverse proportionality, if you're going to halve the area, you're going to double the extension, right? Half the area, double the extension. So it's going to be half the area, then you double the extension. It's the only thing. If you halve the diameter, it affects the area fourfold. That doesn't work. If you halve the length, that halves the X because they're directly proportional. If you halve the load, that also halves the X because they're also directly proportional. So the answer is going to be A. Question 23. Given the wavelengths of 5 EM waves, and which row correctly identifies the principal radiation for each of these wavelengths? Guys, I'm not gonna lie to you, this is something that you just need to know by head, right? There is no way they're gonna give you the wavelengths, and if you look on this side, I've given you all the wavelengths that you're gonna need. I would really also advise that you just, also read around so that you can be able to just use the things that are coming from your head. But basically, you just need to know them. For example, right? I know that for radio waves, right, they're gonna lie between 1 to 10 to the power of to the power of 6, right? So I have Roy is very ugly except Grace. Okay, so for M is going to be 10 to the power of -3, right? So Robert Mugabe is very RM is very ugly except grace. Okay, straight to the power of -3 to 1, right? And then for this one, it's going to be, for me, it's 700 nanometers up until 10 to the power of -3. Okay, and then for this one, it's 400 nanometers up until 700 nanometers. For this one, it's 10 to the power of -8 up until 400 nanometers. Then for this one, it's 10 to the power of -11 up until 10 to the power of -8. For this one, it's 10 to the power of -14, or anything really, up until 10 to the power of -11. So it basically means that if I look at this, basically my answer is going to be A, because gamma matches, X-ray matches, infrared, sure, microwave fits, and radio fits, right? Very important. Okay, question 24. The diagram shows an experiment to produce a stationary wave in an air column. A tuning fork is placed above the column, vibrates, and produces a sound wave. The length of the air column can be varied by altering the volume of the water in the cube. So you want to alter the volume of the water inside the cube, okay? So the cube is filled with water and then is allowed to run off it. The first two stationary waves could occur when the air columns are 0.14 and 0.42. Okay, so I'm going to copy this diagram, right? Look at the first wave, right? That's going to come. The first stationary wave is going to come like this, right? So it's going to come like this. Sorry. Okay, it's pretty hard to draw it. Let's see. It's going to come like this, right? Like so, then like so. Then the next wave that's going to come is going to come like so, like so, like so, right? So basically like this. Look at this point, okay? This, from the question, this is 0.14, right? And then this is 0.42, okay? So it means from this to this is basically an important structure because this represents node, right? Then that represents a node. So it means that from node to node, right, I already know that this is half lambda. So in this case, half lambda will be 0.42 minus 0.14. That's going to be equal to half lambda, right? So my lambda is going to be equal to 2 times 0.42 subtract 0.41, right? 0.14, like this. So my lambda is going to be 0.56 meters. Okay, so the answer is going to be D. Very important. So whenever you're given vibrating questions, especially with water, always look at before. The first one is going to be just a quarter node, right? So it's an antinode and a node. Then the second one is you're going to form a full thing. The third one is going to form another full thing. So if it was the third time, the third station would be something like this, the fourth, the fifth, so forth and so on. Move on to the next question. The diagram shows the vibration of the displacement x of a gas molecule as a continuous sound wave passes through a gas. The velocity of the sound in the gas is 330. On the graph below, I have the same 0 time as the graph above. What is the displacement time graph for a molecule that is a distance of 0.16 meters further away from the source? Okay, so first I need to know what exactly is the wavelength for this scenario. Okay, I know that V is going to be equal to F lambda. Okay, but I can find F, right? F is going to be equal to 1 over T. But if I look at this, it's 1 over 500 times 10 to the power of -6, right? 1 over 500 times 10 to the power of -6. That's going to give me 2000. Okay, so that's going to give me 2000. So it means that lambda is going to be equal to 330 divided by 2000, and that's 0.165 meters. Okay, so if a molecule is a distance 0.165 meters, it basically means that the phase difference is 0, right? The phase difference for these molecules is going to be 0, right? The molecule that is further wavelength away and the molecule that is not, they're going to have a phase difference of 0. And what this basically tells me is that if one particle is moving up, the other is also going to move up. So these graphs are going to be identical in all regards because they represent particles which are in phase, experiencing the same displacement at the same time. So the answer is going to be D. Very important. Move on to question 26. It's a Doppler effect. We're given an ambulance. So an ambulance is coming and it's giving off its siren with a certain frequency of 600. The speed of sound is 330, and the ambulance is traveling with a constant velocity of 25 towards an observer. Okay. So which overall change in the observed frequency takes place between the times at which the ambulance is a long way behind the observer and when it's a long way in front of the observer. So we're going to talk about the Doppler's effect for a while. So basically how the Doppler effect works, okay, so the Doppler effect, we have an equation for the Doppler effect, right? So the equation for the Doppler effect is as follows. The observed frequency is going to be equal V over V plus Vs multiplied by the frequency of the source. So it's plus or minus, right? But, okay, we have two conditions for the Doppler, right? It's the first condition that must be met is that it's V, okay, V plus Vs when you're moving away, okay, so this is away from observer, okay, then it's V minus Vs when you're moving towards, right? So here you'll be moving towards the observer. Okay, so the question just wants me to compare the change before and after. So I'm just going to calculate both the lower and the upper. Okay, so it's going to be F naught max. Right, what is the maximum frequency that I can get? And I know that the frequency is going to increase as I move towards the source. So it's going to be the first V that I have is 330 divided by 330 plus 25. Okay, times 600, which is my initial one. Then that's going to give me 557.74 hertz. Okay, then I'm going to have F min, right? Then I'm going to have F naught min. That's going to be 330 divided by 330 minus 25 times 600. Okay, sorry. So I'm going to have F naught min, right? So F naught min, that's going to be 330 over 330 plus 25, which is going to be times 600. That's going to be 557.74. Then I'm also going to have Fn max, right? Or the observed frequency, which is the maximum observed frequency that we can get, right? So if I'm going to calculate this, it's going to give me an answer of 649.18 hertz. Okay, so the delta change in the frequency itself is going to be equivalent to 649.18 minus 557.74. Then the change is going to just be 91 hertz. Okay, so the change is going to be equivalent to 91 hertz. Where is it? Here, very important. Okay, 27. Diagram X and Y show the passage of water waves around an obstacle and through a gap. So basically, what is diffraction? Diffraction is the spreading of a wave into the geometrical shadow when it passes through a gap or past an edge. Okay, so my advice to you is you're just going to have to understand the definition of diffraction, and it should show you that both of these diagrams actually show diffraction. This one shows diffraction through a slit. Okay, so it shows diffraction through a slit, but this one shows diffraction past an edge. Okay, so the other one is past an edge, then the other one is through a slit, but they are both showing diffraction. Right, so it's very important for you to be able to distinguish that, because this is an edge and then this is also again an edge. Right, so if two edges, and then it's still just going to show diffraction. So both A and B, or X and Y, illustrate diffraction. Okay, a rope is fixed, the other end moved up and the other end down, setting up a stationary wave. What is the phase difference between particles at X and particles at Y? Lock in. You need to understand this, guys. We have a node, then we're going to have an antinode. It's always a fact between, okay, between two nodes, okay, between two nodes, the phase difference, okay, the phase difference is 0. Okay, and I'm going to explain why. Right, then from one antinode, okay, from one antinode to another, right, so from one antinode, right, to another, the phase difference will be equal to 180 degrees. So particles which are inside a node are going to experience the same displacement at the same time. If they're all moving up, they're all moving up. If they're all moving down, they're all moving down. So it means that if there's a phase difference between x and y, how would this shape be maintained? Because others are moving up, others are moving down, it won't work, right? So it means that for this shape to be maintained, for it to be stationary, they need to be moving the same thing up and down, and it's going to be having a phase difference of 0. But between this and this, right, they have a phase difference of 180. If others are moving up, these ones are moving down, these are not moving up. So it means that, you know, you can always think of it that way, right? This one, sorry, if this one is moving up, this one will also be moving down, right? But if you look at this down and down, that's just going to be also in phase with 360, right? But what's very important is to say, whenever you're inside between two nodes, the phase difference is 0. From one antinode to the next adjacent antinode, the phase difference is 180. And if you know that, you're done. So if you're going to have antinode 1 and antinode 2, let's say antinode 3 like this, it's going to be 1 from this to this 180, from this to this 360. That's basically how you do it. Okay. Question 29, it's a diffraction grating. Whenever you see the word grating, what I always do, I just start with my formula, right? Whatever they're going to give me, it has to use this formula somewhere, somehow. Okay, so what do I want to find? I want to find the wavelength. This saves time. I don't even have to read the question, right? Lambda will be equivalent to d sine theta, okay? D sine theta divided by n. Now let's read it, right? The spacing of the slits is 1.15 times 10 to the power of negative 6. So d is 1.15 times 10 to the power of negative 6. Theta is always from the 0th order. So theta will be 30. So it's sine 30 divided by n. N is how many, what order are you? It's the first order, so n is 1. So basically, we just have 1.15 times 10 to the power of negative 6 times sine of 30. And that's 5.75 times 10 to the power of negative 7 meters. That's basically 575 nanometers. The answer is C. Question 30, this electric fields, no longer do them. 31, electric fields, we no longer do them. They're out of the syllabus. Question 32, also electric fields outside of the syllabus. Question 33, an electric kettle is marked 3.10 kilowatts and it is used with an electric supply of 40. So what am I given? I'm given power. Okay, so I start by writing what I'm given. I'm given that power is 3.10 times 10 to the power of 3 watts. Then I'm given voltage, V, is actually going to be equal to 240 volts. But I know that power is going to be equal to VI. So it means that I is going to be equal to power divided by V, which is 3.10 times 10 to the power of 3 divided by 240. That's going to give me an answer of 12.9. Okay? So the answer is going to be either C or D, but these two guys are definitely wrong. But I also know another relationship. What other relationship do I know? What other relationship do I have in my arsenal? I also know that P is equivalent to V squared divided by R. So R is going to be equivalent to V squared divided by P. So I'm going to have 240 squared divided by 3.10 times 10 to the power of 3. Then that's going to give me 18.6 approximately coulomb ohms. And my answer is going to be C. Very important. But question 34, a thick copper wire is connected to a thin copper wire in a series with a cell, as shown. What is significantly less in the thick wire than in the thin wire? What is significantly less? Okay, let's think. We can create equations and then compare. How would the equations look and what equations do we know? So if I'm given these two things, I know that based from the question, I'm seeing drift speed, I'm seeing number density. So somehow I need an equation that connects all this stuff. How do I find it? Okay, let's derive it. Okay, I know that Q is current times time. Okay, so I is going to be equivalent to Q divided by T. But I know that Q is going to be N times E, right? E is 1.6 times 10 to the power of negative 19 coulombs. One electron, one charged particle, carries 1.6 times 10 to the power of negative 19. So if you have N of them, that would be your charge. So I is going to be equivalent to Ne divided by T. But I know that my number density is basically the number of particles that I have per unit volume. Density, mass per unit volume. Number density, number per unit volume, right? Number of particles per unit volume. So N is going to be equivalent to N times V. So I can remove N in that equation. So my I is going to be equivalent to N times V small n times E divided by T. But, okay, very important guys, but volume is equivalent to area times length. Okay, therefore I will be equal to N times the volume, which is the area, times the length, times E divided by the time. But if you look at this, if you have L and if you have T, that's going to be V, right? So I is going to be equal to N A V E, right? So I is equals to NAV N A V E, where N, right? Let's just define the terms here, where N is the number density, right? So N is the number density, okay, and A is the area, and then V is the drift speed or the drift velocity, the average speed that these particles are moving with. Then E is the elementary charge. I've already defined E, so E is the elementary charge. Okay, this was all just to prove this fact. I is equals to NaVe. But how do I make a relationship? The thick wire, okay, I know that I is going to be equal to NaVe. The thick wire is going to have a bigger, okay, a bigger A. But if I is constant, since they're in series, if N is constant, same number of particles, basically, it means that V has to be smaller, because A, since they're on the same side, right, A will be inversely proportional to 1 over V. Why? Because E divided by N times V times E is going to be equal to A. All of these things are constants. All of these things are constants. So A will just be related to V, right? Okay. So let's think about this, guys. The bigger the area, the smaller the speed that they're going to travel with. So it means that the thing that's going to be significantly less is just going to be the drift velocity that's going to be present. And I want you to think about this. A bigger wire means that the particles are not going to move so much, right? Imagine you have people moving in a congested area. People are going to move very, very fast, because it's like, well, there's a very limited space, right? We have to move, we have to move, we have to move. Electrons feel the same pressure too. But if the area is very big, the electron will be like, okay, if you want to move fast, just go above me, right? There's space, move fast there, right? Then that electron is going to feel lazy if another electron is going to come. So they're just going to move very slowly, because they have so much weight, they have so much freedom to move. But if the area is very small, like in the thin wire, the electrons are going to be moving very, very fast. Like people in a very tiny spot, they're going to be moving very, very fast. So basically, if the area is bigger, the speed is also going to be smaller. If the area is smaller, the speed is going to be faster, but they have to move fast so that everyone can get a chance to move in order to maintain the current. That is what it basically implies. Okay, question 35, we want to find the magnitude of the resistivity of copper. There are two methods, guys. Lock in. It's either you have crammed this, right? Okay, I don't like it, right? I don't like cramming physics. I think the way physics should be learned is understanding of concepts, right? You can cram it because you can know, for example, like the Young modulus is something that you're just supposed to know, that the Young modulus of copper is 10 to the power of 11, right? That magnitude. But with the resistivity, you could also know it. It's like 10 to the power of -8. Google it online. If you're going to Google what is the resistivity of copper, it's going to pop up. It's going to be 10 to the power of -8. So if as a student, if you just know it at the back of your head, that the resistivity of copper, most metals also range in that range, you can be able to solve it. But how I was thinking of this, I was like, what if I didn't know, right? That is what was intriguing me. That is what, kept me up with this question itself. You say, what if I didn't know? What would I do? Then I started to think, and I came up with an idea is going to be equal to rho, which is the resistivity, right? The length divided by the area. So R times A divided by the length should basically give me the resistivity. But I didn't know what resistance to use. So I went back here. They gave me an electric kettle. And I was like, sure. An electric kettle probably is made up of some metal, right? Might not be copper. Probably is going to be another metal that's going to have a very high resistance. But this is a pretty close one. Then I said, let me use 18.6 as my resistance, right? So I was using 18.6. Then I was like, okay, my area is going to be pi d squared over 4. Right? And then I assumed that the length of this wire might be, I don't know, 0.5 meters, right? It's a wire in a kettle, that coil that you see in a kettle. Then I said the area of that thing, okay, might be just, I don't know, 1 centimeter. Sorry, okay, it's going to be 1 times 10 to the power of -3 divided by 2. Right, then I said I got an answer of 2.92 times 10 to the power of -5. Then I said it's definitely bigger than 10 to the power of, less than 10 to the power of 2, definitely smaller than 10 to the power of -3, but not as big as 10 to the power of 13. Probably my resistance value is off. Maybe the resistance is actually much lower than this. I settled with B. Or maybe the length is not even that big, right? But I used reasoning to say, I have a certain resistance that they have given me. How can I calculate this? Resistivity is resistance times area divided by length. I found an area, just estimated. I used the resistance that they'd given me above. I couldn't just think of a resistance on my own, but I used something that made sense. Then I assumed that it might be half a meter long. Then I calculated and I got this. That helped me figure something that is very close to the answer. But if that's hard for you, just remember it at the back of your head. Resistivity of a copper, of metals, mostly is usually 10 to the power of -8. And if another question comes like this in your paper, you'll be fine. Move on to question 36. In this, we've been showing the reading on the ammeter being 0. So it probably means that the velocity at this point, right, the velocity at 1 and the velocity at 3 is going to be equal, right? It means that V1 is going to be equal to V3. Why? If they were not equal, it means that if they were not equal, what did you tell me? That the ammeter will not be 0, because current flows from high potential to low potential, but current can never flow if potential is equal. Why does it need to flow? Potential is equal, right? Both potentials. So it means that V1 have to be equal to V3, but V1 basically refers to the share of voltage that R1 gets. So that's going to be R1 over R1 plus R2 times V, right? And then for this one, it's going to be R3 divided by R3 plus R4 times V. These are going to cancel out. I'll be left with R1 over R1 plus R2 is going to be equal to R3 over R3 plus R4. So I'm going to have R1, which is going to be R3 plus R4, which is going to be equal to R3 R1 plus R2. So I'm going to have R1 R3 plus R1 R4 equal to R1 R3 plus R2 R3. But this is equal, right? This and this are equal, so they cancel out. So basically I'll be left with the final answer of R1 times R4, which is equal to R2 times R3. Okay, the answer is going to be D. How are you supposed to know this? I'm going to tell you a little secret, guys. there is no teacher on earth who might come, or unless you have, I don't know, a very nice teacher, maybe a YouTube physics teacher or something like that, that's going to tell you or give you notes in class as to all of these scenarios and how they're supposed to be worked out. Who's gonna come and say the current is zero, solve it in this way. If you see this, solve it this way. There are a lot of concepts in physics, so it is up to you as a student to browse through a lot of question papers, write well detailed notes. Right, this is my advice. I think with these questions, a person would know that the reading of an ammeter is zero if they had encountered a similar question that required them to use a similar concept. Because this is asked in paper 1, paper 2, a lot of questions where you have to apply this concept. So my advice would be, do a lot of past papers, right? And when you get these solutions like these things that I'm giving you, right? Or you get it from other YouTubers, or you get it from websites, write them down in well-detailed notes. You might write the paper code, write the question down, and explain it in your own words. The the voltage is equal at point A and point B, meaning that the resistances have to have a ratio, R1 over R1 plus R2 times V. Then how do I connect it? How do I get to the final answer? You get it, and then you're able to work it out. So, guys, and then there are also other tricks, right? Other tricks that, like the diamond rule, right? I'm just going to give it to you. It means that if you have a certain point A and point B, right? And then the ammeter reading is zero, the resistances will just be the product of the diagonals. So this and this and this and this. R1 times R4 should be equal to R3 times R2. That only applies if the ammeter reading between 4 resistors is zero. That's a shortcut, right? I don't need to do all this, but I need to do it so that I can gain understanding, right? But most of the understanding comes from working questions and writing well-detailed notes that will help you in the future. Just working these questions on a piece of paper that you're going to throw away will not help you, because if an exam is going to come requiring you to apply this concept, you probably won't know it. So my advice to you guys, please have well-detailed notes that help you write physics. Physics is very fun, but I think that it's not really taught in a way that gives you everything you're going to need. And is it up to you as an AS student to read on your own? And if you realize most of these questions, if you look at most of these questions that we're solving, no teacher is going to come in class and says, how does this vary? If the area is bigger, the velocity, unless you have, again, a physics YouTube teacher. But, no teacher is going to come and say, I don't know, let's look at, like, for example, this. It's going to come and say, okay, d sine theta is equals to n lambda, but if there's going to be a scenario like this, do this, unless your teacher is very generous, right? Or like maybe, I don't know, if you remember where it was ever mentioned in your class, probably that phase difference is zero, right? When you're inside a node, right? Probably was mentioned, probably wasn't, but it's up to you as a student to research, to write notes, and be able to get a pass in A-level physics. It's very possible to pass A-level physics, but it needs work. It needs a lot of effort, and it needs you to be very organized and write well-detailed notes, right? Sorry for, getting a little bit carried out, but it pains me a lot when I see students who always ask, how can I be able to understand physics better? And my advice to them is always, do questions, right? Have notes, use your syllabus, use your textbook, but as you're doing questions, document them, right? In your notebook, document them down so that you can be able to understand and actually solve problems, right? So sorry for that, but I feel like it's something that needs to be addressed. Just going on YouTube, getting a free video or free video solution is not going to help you unless you're going to make notes from this, right? This is a fact. If you're going to have this in your notebook, if another question comes, it might be a different arrangement. You're going to know this because you've written it somewhere, and when you're reading the night before an exam, you're going to use these notes for your as your assistance, right? Very important. Okay, move on to question 37. This is an application of Kirchhoff's. Okay, this is an application of Kirchhoff's first law. Okay, what does it say? It says that the sum of currents entering into a junction is equal to the sum of currents exiting the junction. This is popularly known as the law of the conservation, right? The conservation of charge. Okay, charge is always conserved. So if we're entering a junction, I1 should be equal to I2 plus I3. The answer is A. Move on to question 38. What is a proton? Guys, a proton is a hadron. Lock in. Is a hadron why? Because it experiences a nuclear force. A hadron is a particle that experiences a strong nuclear force. A particle that experiences a strong nuclear force. Okay, if a particle has 2 down quarks and 1 up quark, that's probably a neutron. And then quarks are not fundamental, right? And quark is not a lepton. A lepton does not actually experience a strong nuclear force. And these include, I don't know, electrons and all that stuff. So the answer is A. What is the correct description of gamma radiation and beta minus radiation? Gamma radiation is basically electromagnetic radiation, and beta minus radiation is basically a high speed nucleus. So the answer is going to be C. Move on to question 40. We've been given a series of decay equations, and 3 successive decays are occurring. The first decay equation is the emission of a beta minus particle. Then the second decay results in the emission of an alpha particle. The third decay results in the emission of another beta minus particle. So it means that, let me assume that P is 40, then this is 20. So if it's going to undergo beta minus decay, it's going to be 40, right? So it's going to be 21, it's going to gain a proton. And that's going to be 0, -1, and beta minus, right? So this becomes that. Then if it's going to emit an alpha particle, it's going to be 36. Then this is going to be 19 of Q, right? Of R, sorry. So it's going to form R, right? And then this was Q. Okay, so it decayed and formed Q. So Q decays and forms R. Okay, that's cool. Then it releases a helium nucleus, and then that R is then going to decay, right, and form S, but it's going to now be 20. Then this is going to be 36 plus 0, -1, and beta negative, right? But if you look at this, we now want to compare. We basically want to compare P and S. So I'm going to take P. Okay, I want to take P. Here is P, and put it here. Then I'm going to take S. Okay, here's S. And then put it here. What's similar? What's different? They have similar proton numbers, like here, proton number 20 and 20. So basically, they're going to be isotopes, same proton number, but probably different neutron numbers, right? So they're going to be isotopes, same proton number, but different neutron numbers. So the answer is going to be B. That is it, guys. Thank you for watching this video. I hope it was very helpful. If there's anything that you found interesting, please do put it in the comment section, and please do like and subscribe. And remember to always, practice a lot of questions. Be intentional when you're writing your notes. And I hope that everything will be okay. #be intentional, and I'll see you in the next one.